let's officially start this Bose Colloquium. So welcome all to this Bose Colloquium lecture that will be delivered by Professor Uwe Boversiepen from the Faculty of Physics, University of Duisburg-Essen. So to briefly introduce Professor Boversiepen, he did his PhD in experimental physics from the Free University of Berlin in 2000, and in 2005 he did his habilitation from the same university, that is the Free University of Berlin. And since 2009, he has been a full professor in the University of Duisburg-Essen. And since 2016, he is a spokesperson of the Collaborative Research Center 1242. He has received awards like the Heisenberg Fellow of the DFG, and the Carl Schill Award in the Physical Society of Berlin. The research interest of Professor Boversiepen includes femtosecond magnetization dynamics, non-equilibrium dynamics of correlated electron materials, and ultrafast electron dynamics in low-dimensional systems. So I understand that many of our faculty members and the research scholars will be interested in the topic he is going to cover today. And the title of Professor Boversiepen's talk is Microscopic Dynamics of Propagating and Localized Excitations across interfaces analyzed by femtosecond solid-state spectroscopy. So it's our privilege to have Professor Boversiepen within us, and I request Professor Boversiepen to please deliver the lecture. Professor Boversiepen.
Yeah, Rajiv, thank you very much. It's a pleasure to speak to you today. So step by step, traveling becomes possible, as we just discussed in the last couple of minutes before my talk. But Kolkata is certainly a long distance travel, and I'm therefore happy that I can speak to you online today. So in our physics department, and you see the photo of it in front of you, we run this collaborative research center on, oops, what has happened now? Presentation has stopped. I have to start this again. So can I just, now it works. So now you should see my second slide, yeah? Yeah. So here in our Faculty of Physics, together with Faculty of Chemistry, we run this collaborative research center on non-equilibrium dynamics of condensed matter in the time domain. And the key element of this effort is to have external stimuli that drive dynamics in condensed matter. And typical external stimuli are these femtosecond laser fields, but we also have electrical field pulses or ion pulses that we use to stimulate this dynamics. And then this dynamics is investigated in 3 different project areas. And we have, for example, rather small systems where the size of the system is on the nanometer scale and is smaller than some relevant interaction length. So here we study local relaxation and isolated excitations. In another project area, we now have larger systems, and this dimension becomes larger than the interaction length. So here we become, we investigate propagation effects and extended excitations. And you can, for example, think about the problem that you have a heterostructure and you can inject an excitation across an interface. And finally, we investigate structural and cooperative dynamics. So this external stimulus then changes, for example, the size of the material, the symmetry or lattice constant, or internal pressure. And I will show you examples for these different project areas. But before I do this, let me introduce the non-equilibrium that we investigate. And as I've mentioned, we have various kinds of external stimuli, but I will focus today on femtosecond laser pulses. And as an example, I show you here a Fermi-Dirac distribution function at low temperature, and consider in a strongly simplified picture the absorption of light with frequency nu here basically below the Fermi energy, where we excite holes by bringing electrons to excited states above the Fermi level. And this is a strongly non-equilibrium distribution that we generate. And since there's electron-electron scattering as a very likely interaction process going on, we have quickly after the excitation this non-equilibrium washed out distribution. And if we even wait a bit longer, electron-electron scattering gives rise to a Fermi-Dirac distribution again. However, the electronic temperature is expected to be way larger than initially. And now we can discuss whether it's only the electrons that have interacted at the time scales, or we have also to take lattice excitation or spin waves into account. And there's a very simple model that I will introduce now that considers that the hot electron temperature interacts via electron-phonon coupling with the lattice. So this model suggests this picture that we have the hot electrons in the presence of a cold lattice for a very short moment of time. And this two-temperature model consists out of the description of the electronic system by this electronic temperature and the specific heat, as well as the lattice-specific heat and the lattice temperature. And it's essentially two coupled differential equations. So the first equation for the electrons has here the source term, that is the laser pulse that brings in energy, and the model assumes that all the energy excites the hot electron distribution. So this microscopic details that I just introduced is not part of the model. And then there is dissipation because of electron-phonon coupling. So energy is taken out of this electronic system. This is the negative sign here, and put into the lattice. So this is electron-phonon coupling. And then the model usually also considers electronic transport. So there is a gradient in the electron temperature that then drives this transport. If you solve this equation for typical metals, transition metals, for example, what you find is that the temperature on the vertical axis here as a function of time, which is given here in picoseconds, has this behavior where the electronic temperature shoots up very high. This has to do with the small electronic specific heat that is here included in the model. And then the cooling of these hot electron, of this hot electron temperature by electron-phonon coupling increases the lattice temperature, and within few picoseconds, the two temperatures have equilibrated. And this initial period where the electronic and the phononic temperature are different, this is certainly a strong non-equilibrium situation, and the dynamics are determined by electron-phonon coupling as a microscopic interaction. So we can analyze the electron-phonon coupling. We can look for means to modify it, for example, by modifying the material. And maybe this gives us also some opportunity to control such interaction. But let me emphasize, the electron-phonon coupling is just one example, and you will see others during the talk. Now, why is this femtosecond time scale important? And I start here very fundamental. So this is a slide from my lecture, which is in German, but I think you will understand the key elements. So this is here Max Planck, and here you see an image of the black body radiator, and I discuss here the spectral energy density emitted by the black body radiator. And Planck did quantify the energy spectrum of the local oscillators in these black body walls, and he introduced the Planck's constant. And if you look into the units of the Planck constant in microscopic units, you find this is electron volt times femtosecond, and it's 4.14 electron volt times femtosecond. So the femtosecond is the relevant microscopic timescale. We can have another approach to the femtosecond timescale, which also dates back more than a century to Drude, yeah, so 1900. And Drude described the electrical current density proportional to the electric field by the conductivity. And Drude's contribution was that he said the conductivity is proportional to an electronic relaxation time tau, and there are constants which are material constants. And Drude described this electronic relaxation time as the time between individual scattering processes of electrons with ion cores. I mean, nowadays we know that this is not the correct description, but what is interesting is the following. We can measure the electrical conductivity. For example, here I show data for 77 Kelvin, and from kappa you find that this electronic relaxation time is several hundred femtoseconds. For lead, this is only few femtoseconds. So on the femtosecond time scale, scattering processes occur in metals. And the microscopic nature of the scattering process, as I've mentioned, is certainly different. So I list here quite a number of scattering processes between microscopic excitations of several degrees of freedom. We can also look at the dispersion relations of phonons and spin waves. So I'll show here an example of gadolinium, which is a ferromagnetic rare earth metal, and here you see the change in momentum. This is the frequency scale, and the red data, these are the spin waves and their dispersion, and the black lines, these are the phonons. And if you look here to the frequency, this is terahertz. So we have several terahertz at these bosonic frequencies, which means that the period of this excitation is in the range of several hundred femtoseconds. So again, the femtosecond time scale. And by these few slides, I hope that I could show you that microscopic excitations proceed on several to several hundred femtosecond time scales, and time-resolved spectroscopy in the solid state, then if one accesses these time scales, promises to get microscopic information. Now, an important question is, how do we reach this femtosecond timescale if we want to do these experiments? And there's a simple answer: use light. And just to emphasize this statement, I show here work by Ferenc Krauss and co-workers from a couple of years ago, where they could show in a time-resolved experiment, in fact, this was an attosecond time-resolved experiment, the temporal variation of the electric field in an 800 nanometer laser pulse. So if we have 800 nanometers, which we can measure by a spectrometer, we can simply calculate by the known velocity of light that the frequency is 4 times 10 to the 14 hertz. And what you see here on the vertical scale, this is the electronic kinetic energy measured using photoelectron spectroscopy after emitting photoelectrons and then letting it interact with this electric field of the laser pulse. And we can read off the periodicity of this light, which is 2.5 times 10 to the minus 15 femtoseconds. So you can clearly see the femtosecond time scale. And this was very seminal work, which also made it to a well-known physics textbook here in German language. Now, how do we generate these femtosecond light pulses? And this is a very simple principle that I would like to mention here. This is simply going back to the superposition of modes. And I show you here the superposition of two modes. This is something you all know. There is this beating occurring. Now simply take more than 2 modes, for example, 8 modes. And you see already with these 8 modes, you have a piling up of intensity at well-defined times and a loss of intensity in between. And if we consider that the duration of those pulses is determined by a time bandwidth product, so to get a certain time duration delta t, one has to provide a certain spectral bandwidth delta nu, and this is simply a constant here. So now there are various well-known laser crystals that can provide such femtosecond laser pulses, and one example is the titanium sapphire laser, where you have a titanium ion that vibrates in a sapphire matrix. And this vibration is plotted here along this Q coordinate, and you see here the ground state, these T2G orbitals, from which you can absorb in a rather large bandwidth into the excited E2G states. The fluorescence is shifted because of the Stokes shift into a regime 600 till 1000 nanometer, and you can see already that this emission is broadband. So you can read off the spectrum that the bandwidth in wavelength is 200 nanometers, which then converts to a bandwidth in the spectral domain, which is 10 to the 12 per second. And this then, according to this time bandwidth product, provides access to femtosecond laser pulses with durations of only few femtoseconds. But now we have to realize this in a laser cavity. And a laser cavity can typically maintain several thousand to 10,000 modes, so it's sufficient to really provide bandwidths and get femtosecond laser pulses. If you do this in a simple cavity, you work in energy per pulses of several nanojoule, but with amplifier schemes, you can get up to a joule or even more. And for this amplification, Gérard Moreau and Donna Strickland, these are the pioneers who have investigated this, who have introduced this amplification, got in 2018 the Nobel Prize in Physics for their method of generating high-intensity, ultra-short optical laser pulses. And we stand on the shoulders of those giants and exploit this in our research. Now, let me make a comment. These are very intense pulses, and we bring them to our sometimes delicate samples, so we have to worry whether these samples are stable, and in a way we hammer on the sample. I will come back to this point. Now, how do we detect the femtosecond response? And if you simply take a photodiode, you all know that there is an ohmic resistance and a capacity in this diode, and the respective time scale is typically longer than 10 picoseconds. So we cannot use this for this ultra-fast spectroscopy. What we rather do is a cross-correlation measurement. So we measure this cross-correlation as a function of time delay between two laser pulses. And this is this cross-correlation. So we have a known laser pulse and we have a response in the material that is triggered by a replica of that known laser pulse. And you can view this as it is indicated here by gating the response of the material driven by this first laser pulse with a time-delayed pulse. And we measure here the dependence on this time delay in pump probe detection. And what we assume is we can now do this with a laser repetition rate. And the idea is that we suppose that identical events are captured at these subsequent moments. And this is non-trivial, and one has to realize these conditions with quite some thought. But I will show you several examples where this works really well. So let's start with a simple example, acoustic wave echoes. So we take a thin film of thickness d, which is larger than the optical absorption depth of a pump laser pulse. So we only excite here within the optical penetration depth some region of the sample. Then there's a gradient in excitation, and after some time, this excitant region has started to propagate into the material according to the group velocity of the formed wave packet. If it reaches here the backside, it cannot propagate further, it will be reflected. So we have some echoes. And you can measure this in a rather simple linear reflectivity pump probe experiment where you monitor the change in reflectivity as a function of pump probe time delay. This is here done with picosecond and time resolution. And if you change the thickness of that film, these are gold films, you find that the thicker the film becomes, the longer the period in this echo is observed. And you can analyze here the periods, the minima and maxima at their respective pump probe time delays, and plot then the duration of these periods as a function of the film thickness. These are these individual data points, and then determine the velocity of this propagation from such a measurement. And if you compare the result, here this work in the PhD thesis from more than 20 years ago has obtained this 3,310 meters per second. This compares pretty well to the literature value of sound, of the sound velocity in gold. All right, so let's get back to our research program. So I will now give you some examples of highlights on our collaborative research center, and then move on with work here from my own group. And the first work that I would like to highlight is work by our principal investigator, Klaus Sokolowski-Tinten, who has investigated the heterogeneous to homogeneous melting transition using ultra-fast electron diffraction. And look here at these data. These are the transmitted diffraction images shown here as a function of increasing absorbed energy density, and here with increasing time. And if you look at these diffraction images, for example, here to the one at the top left, you see a diffraction of a single crystalline material. But if you look at the other end, for example, here you find a diffraction image of a liquid. So we have molten, or Klaus has molten with this laser excitation, the gold. But you can also see here images where you see a superposition of the crystalline and the liquid material. And this is what they were interested in. So they looked in their analysis to the dependence of this melting time as a function of the energy density. And in this high energy density regime, you see here that these melting times agree very well with these dashed lines. And these are molecular dynamic simulations that are based on this two-temperature model. But if you go to this intermediate energy density, then you see that the experiment deviates from the simulations. And this has to do with the liquid-solid coexistence that they have observed here. And they basically conclude that for a good understanding, these models have to take also these coexistent problems into account. Now, let's move ahead and discuss work by Frank Meyer zu Heringdorf and his team. And he looks at some femtosecond dynamics of orbital to angular momentum conversion in nanoplasmonic vortices. So what is meant by this? Let me remind you to a simple grating coupler. Yeah, so where you can, by appropriate resonant electromagnetic fields, which are polarized perpendicular to this grating, emit surface plasmon polariton wavefronts. And now we go from this simple grating coupler to an Archimedes spiral. This is shown here. So this basically is designed such that upon 2 pi, there's a resonant condition fulfilled that the wavelength of the surface plasmon polariton exactly matches into here. And Frank and his team, they do this by cutting here ion milling into these gold nanostructures, these Archimedes spiral. And they use circularly polarized light of the indicated helicity. And just with very simple considerations, we can now look how the surface plasmon polariton wavefront propagates. And you see, because of this resonant condition, upon one optical cycle, we have now 2 times the wavelength between the wavefront in the initial and in the final state. So this has increased the angular momentum by +2 simply by mixing the helicity and the orbit momentum of the Archimedes spiral. And this can be investigated in real time using a pump probe experiment. And you can see here the microscopy image of a photoelectron emission microscope. And with this movie, you now see exactly what I motivated before. So here you see the real data within the optical circle, and the right you see a Fourier transform of the first harmonic. So why is this relevant? Well, just think about fundamental problems like spin-orbit coupling and condensed matter. Here with such an approach where you see the transformation from spin to orbital angular momentum, you can really investigate the timescales related to this. Another aspect of this work is the local field enhancement that you can generate here locally, which goes up to 10 to the 13 watt per square centimeter intensity by such nanofocusing. All right, these are two examples from our center, and I would like, after this introduction, proceed with two pieces of work from my own group, energy transfer dynamics in a metal insulator heterostructure, and local and non-local electron dynamics in a gold-iron heterostructure, which we grow epitaxially on MgO001. And we'll end with a short conclusion. So, by the way, if there are urgent questions, just don't hesitate to interrupt me. Yeah, as far as I understand, we will also have a question and answer session at the end.
Yeah, so we'll have a question and answer session, but if there is any pressing question, so one can raise hand and just ask the question.
Thank you. So, Rajiv, please interrupt me because I don't see what's going on.
Sure, I will.
Yeah. Okay, then let's continue. So I will discuss this microscopic energy flow dynamics in a simple heterostructure. And I've chosen this example because this is based on a lot of collaboration within our center. So we have here several PIs underlined which join forces, and we have here, for example, Andrea Eschenlohr, you see Klaus Sokolowski-Tinten, who I mentioned, Heiko Wende, Katharina Olefs. These are all the experimental PIs involved, and we have Markus Gruner and Rosica Pencheva as theory PIs. We exploit in this work two highly relevant user facilities, which I will mention on the way. But now to the physics. So consider a simple heterostructure consisting out of constituents A and B, and this is repeated n times. Now we locally excite this by absorbing a femtosecond laser pulse in iron, and then you have this local energy deposited, which is then redistributed through the interfaces into the adjacent material, and this is in our case MgO. So we discuss here iron MgO heterostructures. Let's look how this translates into the energy dimension. So we have here iron. Iron is a transition metal, so we have a Fermi level, and this is where we absorb the light. We use here UV light of 266 nanometer because we want to reach the conduction band of MgO. So in principle, we have sufficient energy to inject carriers into the conduction band of MgO and overcome here this energy transfer barrier delta. However, there's a competing process, which is electron-electron scattering, which I've mentioned earlier, which happens in iron, and then subsequently there could be electron-phonon emission to transfer the energy into the adjacent material. These are very thin layers of only 2 nanometers, and we have several in a row in order to perform here in this heterostructure transmission experiments. And we do transmission experiments using soft X-ray spectroscopy, and soft X-ray spectroscopy allows us to probe the oxygen KH. So here you see the transmitted intensity for the oxygen KH that represents here the insulator, and the iron L3 and L2H to represent iron. And with this kind of an experiment in transmission, we can use the UV as a pump and the soft X-ray at the representative absorption energies to investigate the dynamics in the insulator and in iron. Now, this is something that we do not yet have tabletop, but I will show you that we are on a good way to get there. So this experiment we performed at the Bessie synchrotron, where a couple of years ago, together with colleagues, we could set up, due to funding of our Federal Ministry of Education and Research, a pretty sophisticated pump probe experiment, exploiting here the femtosecond laser-induced acceleration of the electrons in the storage ring. So this is the storage ring. Here we have this interaction of the electrons in the storage ring with this amplified laser. Then there's a bending magnet to separate the accelerated and the non-accelerated electrons. And then we have here a radiator which emits the femtosecond X-rays, and all the way down here to experimental stations where we have then also a laser for pumping these samples. So let's look at the soft X-ray spectroscopy without pump excitation at first to understand what we actually start with. So here at the left, you see the absorption at the oxygen K edge. This is the 1s to 2p transition. And you see here the pronounced fine structure of the bulk oxygen K edge absorption in MgO. There is theory, which I mentioned already by Markus Grun and Rosica Pencheva for bulk and interface. And you see here these contributions. And I would like to highlight this small peak here in the pre-edge region. This is a signature of an interface state. At iron, we see the L3 and L2 edge. This match very well with the calculations for bulk and interface. There's a small interface contribution that cannot be resolved since it's here in the white line. So we have here bulk signatures of oxygen and iron that also with this interface signature allow us element-specific and in particular site-specific analysis in our heterostructure. Now, let's go pump probe. So what you see here in the top, this is the absorption at the oxygen K and the iron L3 edge before and after pumping. So you see here before, this is the black dotted line, and the red and the blue line, this is after pumping. So you can see some small differences, and we can plot the pump-induced change here by just calculating this difference down here. And you see we have to struggle to accumulate data, but there are clear signatures that we can find within a given beam time. For example, here we see a drop in the intensity maximum at the oxygen K edge absorption. Here, this is maybe not so clear whether this is noise or a signal. At the iron L3 edge, we see essentially a red shift of this pump-induced change. So this indicates that we see a shift to lower energy and maybe some smaller intensity redistribution. So intensity drop. So what I would like to emphasize is that the time where we see these maximum changes differ by about 3 times. So we proceeded now with the experiment and identified 3 different regions of interest in the photon energy, where we now do a specific time dependence. And this is shown here at this slide. So here you see the time dependent as the iron L3 edge, at the oxygen K edge, and the oxygen K pre-edge region. And without further discussing, at a first glance, you see that within these first 2 picoseconds, the response is completely different. So we probe different processes at these 3 edges. And this highlights that you can really learn a lot if you do this soft X-ray pump probe spectroscopy. But now, how can we discuss the data? Let's start here with the iron L3 edge. There we see a response within 100 or 200 femtosecond, where we see the maximum in the pump-induced X-ray absorption change, and then a drop of intensity. So this might remind you about the 2-temperature model that I introduced earlier, where we have first hot electrons and then interaction and cooling of the electrons because of electron-phonon coupling. So here, this could indeed be due to electron-phonon coupling, and this fast response is the excitations of hot electrons and electron-electron scattering. Now, what do we see at the oxygen K edge? And this is obviously a difficult experiment. We have a lot of noise here, but you can clearly see that there is a delayed response with respect to iron. So this means that this injection from iron into the conduction band of MgO is not a process that we observe. We rather observe this electron-electron scattering and electron-phonon scattering. And Now, the response of the oxygen K-edge is faster than this response which we see due to electron-phonon coupling in iron, but the time scale suggests that we indeed have some phononic dynamics here. The pre-edge dynamics I will discuss in a moment. So if this is indeed a response of the lattice, it would be interesting to look at the lattice directly. And this we can do by an experiment where we transmit short electron pulses through this heterostructure. So I will show you data with electron diffraction. Remember, Klaus Sokolowski-Timpton is an expert on this, and he uses these mega electron volt kinetic energy electrons as short pulses and transmit them through this heterostructure. And this is a diffraction image that he can then record. This is something we do in Northern California at the Stanford Linear Accelerator Lab, where there is this still more or less unique user facility. There is this RF gun, which emits short pulses of electrons here into the sample chamber, and there are two detectors here. So if you're interested, you can look into this reference. So what Klaus analyzes then is the integration once around 2 pi, which shows then here this intensity as a function of momentum transfer Q. And the signal is strong enough that he can also identify changes upon laser pumping the system. Here you see the changes on the order of 1%. I will restrict myself to changes at iron. So iron and MgO have very similar lattice constants, and you can see tiny differences in the momentum transfer. But I will discuss here in my talk the changes at iron, which are here these black vertical lines. At longer delays, like 20 picoseconds here, for example, at larger momentum transfer, we can also identify peculiar changes in the MgO. Okay, so why do we do this experiment? With diffraction experiment, I mean, recall the Debye-Waller effect, for example, we analyze the mean square displacement, delta U square of iron upon laser excitation. And you see here this resulting mean square displacement change upon laser pumping as a function of time delay. And I show you here 4 data sets. First, let's look at those of the heterostructure. This is 5 times 2 nanometers in dark and blue, and here this magenta. This gives the fastest response, yeah? And the data are right on top of each other. What is the difference between the magenta and the blue data? This is the photon energy of the pump pulse. And we compare here the UV excitation of 4.7, where we reach the conduction band of the MgO, and the second harmonic of the titanium sapphire laser, which does not reach to the conduction band at 3 eV. And basically the response is identical. So this means we really have this electron-phonon coupling through the MgO interface, what I mentioned earlier to describe the X-ray data. We compare also to bulk structures of 10 nanometer. These are these slower responding traces, which really means that we probe the energy transfer across the interface. And we can now plot this change of the mean square displacement right on top of our X-ray data. And here on the top diagram, I did this. So this is a second scale where you see the mean square displacement of iron. This is the green line, and it matches pretty well what we observe with soft X-ray spectroscopy at the oxygen K-edge. So think a moment about the situation. So we excite electrons in iron. There's electron-phonon coupling, which determines the green line, the mean square displacement. And on that very time scale, we see already a response at the oxygen K-edge. So this means that there's extremely efficient coupling through the interface to the excitations in the insulator. And we explain this by a so-called electronic Kapitsa resistance, where there's electron-phonon scattering occurring right at the interface. Now, I would also make a comment here to the slower response of the interface state. So this is this dynamics that is clearly slower here in the pre-edge region. So here we have a scenario that is based on heat-induced modifications of the electronic structure and excitation of acoustic phonons. So remember, we probe here a specific feature in the vicinity of the Fermi level at the interface of oxygen. And if we allow for certain changes in the expansion or compression of the lattice, this electronic feature will change its energy, which explains then that this is a feature that is sensitive to lattice expansion or compression. So we can now look a bit more in detail into the phononic density of states. So this is what is plotted here, the vibrational density of states as a function of energy. This goes here from 0, these are acoustic modes, and then you have some higher frequency modes up to 35 millielectron volts in iron. And this is here now in the bulk iron. This is then the interface. Here you have the interface MgO side and the bulk MgO. And what you see at the interface, there are pronounced changes in the vibrational DOS, and we consider here this feature at 15 millielectron volts, which is a clear interface feature. It's absent in the bulk, as well as, for example, this feature here, to be now responsible for this very efficient energy transfer by interface phonons across the interface. Just a comment, so phonon thermalization is usually occurring at very long time scales because this is based on anharmonicity. So the phonons that we use here for the energy transfer, these are clearly non-equilibrium, non-thermal phonons, and these interface phonons, which are populated by interaction with hot electrons, can give rise to this very fast time scale at which we transfer by lattice excitation iron excitations to MgO excitations. Now, to cut the long story short, we start the process by exciting hot electrons in iron. Then within a picosecond time scale, we excite these non-thermal hot high energy interface hybrid phonons at the iron MgO interface, and then on longer time scales, we see at the pre-edge feature thermalization of the heterostructure and the excitation of acoustic phonons. All right, so let me make some intermezzo before I continue with timers of photoelectron spectroscopy. And this intermezzo should show you some of our efforts to bring this soft X-ray spectroscopy to our labs and to make it tabletop. As a side remark, I mentioned that we also work at free electron lasers. April, we have a beam time at the European free electron laser in Hamburg. But now I would like to show you here our effort to make soft X-ray spectroscopy tabletop. And this is based on harmonic generation in atoms. Just as a reminder, you get this harmonic generation if you have laser fields, this is here this red line, that are large enough to tilt the atomic potential. And then you have initially here this tunnel ionization where the electron tunnels out of the atom. Then this free electron is accelerated in the laser field and first taken away and put back onto the core where you find a recombination. And this was pioneered by Paul Corkum, Anne Lullier, and Ferenc Krauss, and for their work they got this year the Wolf Prize in Physics. And we explored this further. And this harmonic emission that is here illustrated has a cutoff frequency, omega c, that is proportional to the intensity of the driving laser pulse, but also to the square of the wavelength. This might be a bit counterintuitive because it means that if you have a longer wavelength, so you go further into the infrared, you get a higher frequency in the emission. But this can be understood such that you have acceleration over a longer time because of the longer wavelength where the electron can pick up this energy out of the laser field. So we exploit this, and we need lasers that operate at infrared region. Remember, the Titan Sapphire laser operates at 800 nanometer, but we want to go further out. And we have developed, therefore, an optical parametric chirp pulse amplifier, which is indicated here. We can read on this laser in this publication. It's pretty sophisticated, so we have a large bandwidth emission of a titanium sapphire oscillator, which synchronizes the OPCPA as well as the power amplifier of our pump. And then we get emission at 3 micrometer as well as 1.5 micrometer. Using chirp mirrors, we compress this light in combination with dielectrics. And we get then here at 3 micrometer, 41 femtosecond at several tenths of a millijoule emission. So this is this 0.6 millijoule. And at 1.5 micrometer, we even get 1.6 millijoule, just a bit more than 50 femtoseconds. And this light we now couple into a hollow core capillary. And here we collaborate with KM Labs, Colorado, and the spectrometer we get from Berlin, IAP. And we then couple this light to a really small diameter. So here you see the focusing, the transmission through 100 micrometer fiber after focusing to 65 micrometer. And then here we bring in the helium gas at rather high pressure, and we analyze the generated harmonics spectrum. And you see it's really tabletop. So this is how our lab looks like. This is the laser. Here we have this is the capillary. Here we focus in the light, and this is the small spectrometer, which we have used for these first experiments. This is certainly work in progress, and I want to emphasize the contribution of Alex Tarasevich, Heiko Wende, Manuel Bridger, and Oscar Naranjo. The sample that I will show comes from Lukas Krelkov and Marika Schleberger. Yeah. So what we detect here as a generated harmonic spectrum is shown here as a blue spectrum, photon energy. So we get a cutoff here between 350 and 400 electron volt. We have a strong absorption at the carbon K edge. This has to do with the contamination of our X-ray optics. And here this increasing intensity, this has to do with the transmission of the beamline. Now we can simply add a sample, so to speak, as a filter, and we use here hexagonal boron nitride, and we see a pronounced change in this region here, and we can now, by normalizing, get out the proper absorption spectrum. The black line is what we measure, and we see here 1, 2, 3, 4, 5 signatures in this absorption. This is the absorption at the boron K edge in hexagonal boron nitride, which is a layered compound similar to graphite, but you have nitrogen and boron atoms in one layer, and we transmit here through a 90 nanometer thick sample, analyzing here the soft X-ray spectrum. Now, what we further have to do is to compare this with literature data and show you one spectrum from synchrotron work where they also identify these signatures, but you can see that the separation of the pi star and sigma star resonances is quite an opposite behavior in comparison to our work, which we currently have to verify that this is indeed due to the well-known searchlight effect that we here transmit in a normal direction, whereas here the other work has been done under 45 degrees, where you then probe in particular here very intensely the pi orbitals. All right, so this is work in progress, and I hope that in the future I can show you more on this. In particular, time-resolved studies is something that we aim at. Okay, let's go to the second part of the work that I would like to share with you. Now we switch gears and we look into gold-iron heterostructures that we grow epitaxially on MgO. And this is work where I would like to emphasize the contributions of Yasin Beyazit as a PhD student, Jan Beckwart as a master student, Detlef Diesing, Florian Kühn, and Jan Mayburg grow these samples, Ping Zhu takes care of the laser, and Manuel Liggis had key ideas for realizing this experiment. As a motivation, I would like to mention work that we have done a couple of years ago, where we did optical pump probe studies of iron-gold-iron heterostructures. And what we do there is using spin currents, so ultra-fast spin currents that we generate by absorbing femtosecond laser pulses in this iron constituent as an emitter. We inject this into gold, and then you have a spin current that impulsively generates spin waves at this second iron layer. The magnetization of those two layers are perpendicular to each other, and this we can probe by a magneto-optical Kerr effect, where we have the probing on the opposite side of the sample compared to the pumping. And this is data here in the magneto-optical Kerr effect as a function of pump-probe time delay, where we see rather complicated oscillatory responses. We can analyze this by doing a Fourier transform, and this blue line is the Fourier transform. So we can identify 1, 2, 3, 4, 5 modes, and those 5 modes match very well with standing spin wave modes that are indicated here in this iron layer. Now, it would be very interesting to learn more about the mechanism under which the spin current propagates. And this is what I would like to discuss now. So the nature of the spin current. Is this a ballistic spin current? Is this a super diffusive spin current? Is this a diffusive spin current? So how can we distinguish these 3 kinds of propagation of these excited electrons that carry the spin through gold? So what you have to keep in mind is that one should discuss the displacement of the electron distribution, sigma square, as a function of the respective time. And this is the diffusion constant. And to distinguish between ballistic and diffusive propagation, one has to consider here the exponent on the time. And this dW, this is the anomalous diffusion exponent. So for dW equals to 2, it is just linear, so sigma square becomes linear in time, and this is diffusive motion. But for dW equals 1, you have a behavior of t to the square, and this is ballistic motion. And super diffusive is basically an intermediate regime of propagation. Now, how do we analyze this? Well, we do a pump-probe experiment. We excite at the back side, and we probe at the front side and detecting now photoelectrons. So we do 2 photon photo emission. We pump electrons in the vicinity of the Fermi level in iron, and we probe electrons on the gold surface at the other side of the sample. So this pump process is basically including the injection across the iron-gold interface, and you see here the nice epitextual structure in this electron micrograph image. Now, the probing that we do is we ionize, we take out the photoelectrons, and we analyze the energy. So this is another way how to represent this. We have the backside pump, we excite hot electrons, which we inject into gold, and then we probe here on the front side with an electron spectrometer. For comparison, we can also bring the pump to the front side and look directly at these propagation effects. So we do a kind of a time of flight like femtosecond 2-photon photo emission spectroscopy. Now, first of all, one has to ask the question whether it works well. And I show you here data. This is the energy above the Fermi level. This is pump probe time delay for 2 different gold thicknesses. So 5 nanometer of gold and 7 nanometer of iron, and a thicker gold layer also on iron for the front side pumping and for the back side pumping. This color scale is the intensity, and you basically see both geometries work pretty well, and we can really exploit this in quantitative experiments. Okay, let's look to the data. And I show you on top here 2-photon photo emission intensity for front side pumping as a function of pump probe time delay. The different colors, these are the energies above the Fermi level. And here in the lower part, you see the backside pumping. Where the 2 data sets agree very well is this slopes in the relaxation. This is a logarithmic scale, so this linear behavior is simply measuring the hot electron lifetimes, and at lower energy, following the Fermi liquid theory, for example, we have a slower relaxation compared to higher energy. So this we understand very well. Where the front side and the back side pumping differ is here in the build-up of the intensity. So here you see that there is a delay for the lower energy, which you can also see here at the maximum, which is absent for the front side pumping. So here we can directly identify those transport effects that I've mentioned to you on the last slide. Just as some additional information, if you vary the iron layer thickness, so this is constant gold layer thickness, variation of the iron layer thickness, we see a drop in the injection efficiency of the electrons from iron into gold. So here simply the intensity goes down. That means the electrons relax already in gold and we have less hot electrons to inject into gold. If we keep the iron layer thickness constant and we change the gold layer thickness, then what we do is we basically modify the relaxation and the transport, which we can see here in the shift of the maximum and these slopes. This is what I will discuss in detail now in the last few slides of my talk. Okay, so we fit the data by a single exponential relaxation convolved with the cross correlation of our laser pulses. So this works pretty well. You can see here for the two thicknesses. So this is this thicker gold layer, 28 nanometer. This is 5 nanometer of gold. And then we analyze the delayed start of the relaxation. This is the red data, which we refer to as the time offset, and the relaxation time tau, which is basically this exponential decay. For the thin layer of gold, we cannot see this time offset being different from 0, but we can see some variation of the relaxation time here going from 2 electron volt to 0.7 electron volt above the Fermi level. For the thicker gold film, we see a very specific behavior of this time offset. It starts really to kick in very clearly at energies below 1.3 electron volt. If we do the backside pumping, for the front side pumping, we have no observation of such a temporal offset. And then you see already here that the relaxation times, these black data, they are different compared to the thin gold layer. I will come back to this. But before I do this, let's compare quantitatively the time offset in femtoseconds and the relaxation time in femtoseconds. So you see here this time offset ranges from 0 to 60 femtoseconds and the relaxation time is from 0 to 100 femtoseconds. So that means while the electrons propagate through gold, they scatter. Yeah? And these are individual scattering processes. Since we see here this relaxation time is on the same order of magnitude as the time offset. So this means that we clearly operate here in a super diffusive regime. So question answered. Now let's go to this discussion of the relaxation time. And I show here reference data from literature for bulk gold, and the red frame is essentially the energy range that we analyze. So let's look here at the low energy part where we see that the lifetime in bulk gold is 120 femtoseconds. And this is longer than for both respective values that we identify here. So how can that be? Do we not have clean gold layers or what's going on? Well, we have to understand that we investigate a heterostructure. So in principle, the scattering probability increases linearly with the film thickness the electron propagates through. And in fact, we consider here scattering in the iron layer thickness, in the gold layer thickness, and in the interface region. And then you can basically integrate this, considering the inverse relaxation time at the respective constituent, which is then the scattering rate. And these rates basically add up independently as suggested by Mathiessen's rule, because spatially these regions are separate. And for variation of the gold layer thickness, we expect to separate two decay processes. And we can simply argue that we have the thickness-dependent relaxation time, which has one contribution in iron and one contribution in gold. And let's check whether this in fact holds. So we now fit our data, which we plot here in this linearized representation with an offset and a slope. If you plot the data over the inverse gold layer thickness, this is what we do here. So you see here the inverse relaxation time, which is the relaxation rate, plotted on the inverse gold time for different energy. And you see this actually works pretty well. So with this linearized representation, we can fit all the energies, and the slope and the offset here now determine this tau 1 and tau 2. And this is what we plot here. So tau 1 is here plotted on this left axis, and tau 2 is plotted here on the right axis. And now let's compare this to literature data for bulk gold and bulk iron. And these are the dashed lines. So the dashed line here in red, this is literature relaxation time in bulk iron, and the black line, this is literature data for bulk gold. And this is what we measure. So in this heterostructure analysis, where we bring in the electrons from iron, inject in gold, and let them propagate through gold, we can investigate buried media, and by variation of the gold layer thickness, we really become able to separate the processes in these two heterostructures. So this is the future impact that I expect, investigating here buried media and interfaces with photoelectron spectroscopy. And one just very brief outlook is we currently work on bringing this toolbox to two-dimensional materials. So basically let these electrons propagate to two-dimensional materials. One example is tantalum disulfide, where there's a discussion going on that is highlighted here, that the stacking should really influence the propagation along the c-axis of this material. And earlier ARPIS study could really not contribute very much because they are not sensitive to these states here above the Fermi level. So this is where we currently are. This is one of these tantalum disulfide crystallites, where with the laser pulse we can basically sit on or beside this crystallite, and this is also work in progress. So this brings me to the conclusion. I hope I could show you that with time domain pump probable experiments, you have a versatile approach to microscopic and dynamic coupling in complex materials, and we also work on quantum matter, which I did not talk about today. And in detail, I discussed energy transfer dynamics and heterostructures, so non-equilibrium dynamics here clearly beyond a thermalized limit. I could show you here this electron-phonon hybrid mode at the iron MgO interface that really mediates via phonons ultra-fast energy transfer. And then I looked into non-local electron dynamics, where we have transport effects and currents in this new backside pumping configuration in two-photon photoemission, which is a novel tool for analysis in buried media. So let me briefly acknowledge the Deutsche Forschungsgemeinschaft for funding our collaborative research center. And here you see part of our large team in a workshop. You see we were outside and kept some distance, so we did not have to wear the masks outside. We hope that we get back to this summer. And with this, I would like to thank you very much for your attention.
Thank you, Professor Boversiepen, for this wonderful talk and informing us about the state-of-the-art facilities that you have been developing and using for this high-end condensed matter research. So now, I think we would like to have some questions from the audience. So I request if anyone has any question, can you please raise your, yeah, Shetty, yeah, please.
Yeah, so thanks. Thanks, Professor Boversiepen, for the nice talk. I have, few short answer questions, let's say. In your first part that, your lab source, soft X-ray source that you are generating in the lab, is at 285 you said you have a carbon contamination. So is there a way to get rid of this to 285 EV contamination? Or?
Yeah, definitely there are ways. So there's work from our competitors, Jens Biegert and co. published last year nice work where they deliberately investigated the carbon K edge. So you can do it. We simply did not make this effort here. I mean, you can, for example, do a plasma etching or UV excitation of your X-ray optics. People are usually a bit afraid because you don't want to have a dispersion device that suffers from this, but this is certainly possible.
Yes, that's true. So one more quick question. So in your first part that you said the thermal energy or phonon transfer from iron to molybdenum oxide, I think, that heterostructure. So is it you said of the order of picosecond? Is it like in many systems is the like of the same order, or it's 1 picosecond is specific to this particular heterostructure?
I mean, thank you very much for the question. I mean, the approach that we have taken here, is let me maybe go here. The approach that we have taken here, in a way, was an approach that exploits the opportunities. And if you have strong covalent bonds at interfaces, in particular between metals and insulators, I would expect that this is a more generic feature. But I mean, you can imagine that this is quite an effort to combine two user facilities, and this is the work that we have done. We have also exploited a bit using this femtoslicing source ultra-fast magnetization dynamics in these heterostructures, but we did not do a case study where we now compare different oxides, for example. But I think this is a more generic feature that we have identified here.
So you think it will be of the order of like plus or minus 1 picosecond of the order of that? Okay. So I have the last question.
We should not stick to thermal models to estimate phononic timescales. They can be much, much faster.
Okay. So I have the last question from the last part. So you pump from one side and then probe from other side of this heterostructure, and you explained that there is a spin wave generation of this process. And in your theory, you discussed about the thickness dependent delay. This theory. So here we see the thickness dependent delay. Then how we are sure that this is due to spin waves?
So can you repeat the actual question? This I did not understand.
Yeah. So I mean, if I see this equation, it mostly talks about the thickness dependent of the heterostructure.
Correct.
So but then how we are sure that the signal that we are getting is actually also related to the spin waves? How do we know there are spin waves?
Okay. Yes, this is a very good point. So we have done previous work that I just quoted here. So please look into this work, for example. So there we have used optical magnetic second harmonic generation to probe the spin-dependent response on the gold surface upon injection of spins from iron onto the gold surface. And we clearly see even the magnetic hysteresis of iron imprinted on the gold surface if you look at the proper time delay. Okay. But I also understand your question such that you say, could we use some photoelectron experiment? And yes, we could if we just have an appropriate spin detector. Then we could simply not only detect here the charge character of the electron, but also the spin character. This we haven't done yet, but this is certainly possible.
So you are thinking something like a more detector that you want to have on the same chamber?
I would rather consider a suitable collaboration because it's not only about the detector, but it's also about the expertise to detect small spin-dependent signals.
Okay. Yeah, thanks. Yeah, I'm done. Thanks a lot.
Thank you, Shetty. Any more questions from anyone in the audience? Professor Boversiepen, then let me ask a brief question that regarding your second part, in which you talked about the separation of scattering in iron and gold. So, is it very specific to iron and gold, or any such heterostructure could be possible?
So again, these experiments are delicate, and it's usually work for a PhD thesis to develop this. And one key idea was early on that we use iron gold on MgO because it's an epitaxial system. So the iron and the underlying MgO have more or less the identical lattice constant. The gold lattice constant matches well if you in-plane orient by 45 degrees. And so this is why we worked now for more than a decade on these iron-gold heterostructures. But you make a very good point. If you now consider that the interface is less perfect, then interface scattering would be important. And this was also a point that was raised by the reviewers of our paper here. And so we have a very detailed response to that question if you look into the supplemental material here. So by varying both thicknesses, so the iron and the gold layer thickness, you would be able to really analyze also this effect of the interface. And this would be very interesting to also compare to other systems. Yeah, thank you for the question.
And regarding this equation, I don't find any specific metal character in this equation. Like, so it only depends on the D, that is the thickness of this interface, and no property of the metal is coming into this equation. So is it universal in the sense?
Very good question. Well, I would rather phrase it this way. For metals, it works very well. If you, for example, consider metal semiconductor interfaces, then bending becomes important. And then you could easily end up at potential barriers that you would have to overcome. So then the whole potential is less trivial than in a metal-metal heterostructure. But nevertheless, it would be very interesting. Yeah. So this certainly is something that we want to exploit further.
Yeah. Very interesting, Professor Boversiepen. And regarding the UV pump and X-ray probe experiment, so you can identify the bulk contribution and the interface contribution separately. So I just missed the point that how can you do that, separate the bulk and interface contribution from UV pump and X-ray probe? And, my question is extended to if in this case you have pump with an UV. So if you pump with, say, a small gap, like you pump with a terahertz, then what will happen to small transitions?
Okay, so let's see whether I got your questions correctly. What I understood you asking is how can we distinguish the interface and the bulk excitation here in the iron MgO heterostructure. So let me emphasize the absorption spectrum, the static absorption spectrum, which we took at the high resolution line. We see this pre-edge feature. So this is the generic oxygen K-edge, but here we see this feature which is absent in the calculation for bulk, the blue dashed line, and for the interface we can see exactly this state coming up. So this is an interface state. So here hybridization between iron and MgO occurs, and we can see it as a feature in the X-ray absorption spectrum. And then basically the point is that in the pump induced change, we focused on these three energies here. Yeah, so this is iron. Here we focused at the two energies at the oxygen K-edge, and we in fact see different responses. Yeah, so this is all becoming possible because we identify this interface feature in the soft X-ray absorption spectrum at the oxygen K-edge.
Yes. Okay.
So you also asked about terahertz. This is,
Yeah.
of course, something we haven't exploited, but colleagues have done that in free electron laser experiments where they combined this with terahertz pumping. So there, the idea is that you do a direct terahertz excitation of ion core motions. For example, you can take some IR active excitation in an oxide and drive this directly. Yeah, so this is certainly possible. It's a bit more challenging to get sufficient intensity for terahertz pumping, but this has been demonstrated.
So the experiments are on. I think it's just the people are doing this kind of experiments. I think. Yeah.
Correct. Yeah.
Very nice. That will be very interesting to watch that how this small transition are going to, being part of with this transition. Terahertz pulse. Very interesting. Thank you, Professor Boversiepen. Any other question from anyone in the audience? If not, then let us thank Professor Boversiepen for this. Yeah, Seti, you have something to say?
No. I'm done. So just.
It was very nice, Professor Boversiepen, to have you, because we had him.
I expected more photo emission data, as I know, which I missed today's talk.
And
I get the opportunity to see more recent photo emission data.
Yeah, we had Professor Boversiepen.
I appreciate this, of course, but if you want to learn something about condensed matter, there is not only surfaces. Yeah, so you can do my talk in my effort to learn more about buried media.
Yes, I see a lot of changes from the day that I had been in the lab and now. Yeah, it's been evoluted to a different. So this soft X-ray absorption spectroscopy, maybe from the last 10 years or so, maybe it is. Professor Boversiepen, I think earlier you were only working on, I don't know, but you were majorly working on photo emission, right? Or photo emission, time result photo emission.
We have started while I was in Berlin to exploit these opportunities at this femtoslicing source. And this has really developed into a major activity in the last 10 years. So we have done this femtosecond X-ray magnetic circular dichroism. We are still doing this. And now we have had a couple of successful beam times at the free electron laser. So Andrea Eschenlohr is here, a PI on several activities. And this is really developing very, very well.
Oh, it's at Bessie. Slicing measurements at Bessie are.
Yeah, so the slicing is active now for, I think 15 or even more years. And more recently, really an effort on the X-ray free electron lasers. So the data that I showed you for the X-ray absorption spectroscopy at the Bessie slicing source, this is essentially what you can get with a perfectly running 2-week beam time. But at the electron laser, this is basically something that you get within a day.
Okay.
Yeah. So the data quality, also the resolution, is like in a static beamline. This is really impressive, the development.
Okay. So this beamline is in Stanford, or I think it's in
Hamburg. So we work in Hamburg.
Desi. Desi. Okay.
X-Fel. Yeah.
Okay, that's very nice. Yeah.
So I did not cover this in my talk today, but there will be more work coming out of this activity in Japan, I hope.
So Andre is taking care of that beam times there in Desi. Okay, that's really nice. Please also convey my hi to her. So Andrea, it would be nice.
Yeah.
Okay. Yeah. So so Mr. Sethi, we thank jointly Professor Boversiepen for being with us and sharing the wonderful lecture. So maybe we look forward to see him sometime in his lab also, and maybe we can welcome, because he was there in the ICC-FM, if you remember, in Kolkata in 2018 December. So he delivered an invited talk in Kolkata. Maybe we can also welcome him once more when the things are a bit normal.
That's true. Yeah.
So I'm usually available for traveling if it is possible. Yeah, so let's see how our planet develops. I mean, these are really not so easy times currently, but let's see how things develop.
Yes.
It would be a pleasure to visit again, I promise.
Sure.
Yeah.
Okay.
Okay.
So thank you, Professor Boversiepen, and we conclude the lecture here. Thank you, Professor Boversiepen.
Yeah. See you then.
It was really a pleasure, and all the best. Good luck, and stay healthy. All the best. Yeah.
Yeah. Wish you the same.
Okay.
Thank you.
Thank you.
Bye.
Thank you. Bye.